In this video, we're going to work through three examples of integrals that can be evaluated using trig substitutions. These integrals are from section 6.2 of the book, which is titled Trigonometric Integrals. And here we have a page from the ebook. This is the page of exercises from section 6.2. And I want to remind you that many of these problems have this pencil icon in the margin, and if you click on that icon in the ebook, it will take you to hints and sometimes a video to help you work through the solutions of these integrals. And I encourage you to use those resources to help you. But let's just glance at the problems here on the page. Let's start by looking at the ones on the left side, and over there I see things like sine to the 7th theta, cosine to the 5th theta. Or the first one is looks like sine squared theta, sine squared x, cosine to the 3rd x. I see an integral secant to the 4th theta times tangent to the 4th theta. Integrals involving trig functions, integrals that you would expect to see in a section titled Trigonometric Integrals. And these should be familiar. These are the types of integrals we talked about on Tuesday, and you had a homework assignment on Tuesday with 12 examples like this on WebAssign. So these are not the types of integrals we're going to talk about in this video. These are integrals that we've talked about before that we should know how to do now, and what we're going to focus on in this video are the integrals in the lower right part of the page, starting with problem 42. Looking at these integrals, first of all, if you should take a moment to try to solve these integrals using u substitutions or methods we've learned already, and there might be one or two that can be done with a u substitution. 52 jumps out at me as one that we might be able to do with a u substitution. That's something you should look for, but most of these integrals are integrals that we have not seen before, that are challenging to do, and the thing that really makes them challenging are these square roots. We should know some similarities in all these integrals. There's certain characteristics, and we'll talk about this in the video. There's certain characteristics that indicate that these might be good trig substitution problems. But what I want you to notice about these, on the face of them, these integrals do not involve trig functions. I don't see any trig functions in these integrals from 42 through 58. But here's the idea. Here's what we're going to do to solve these. We're going to do a substitution to introduce a trig function into these integrals. We will then simplify the integrals, and the objective is to take these integrals and turn them into integrals that look like those that were on the left side of the page of the exercises from 6.2. We'll do a substitution that will bring a trig function into the integral, and then we'll try to turn these integrals into integrals that we saw on Tuesday, things that we've done before. And there's 4 steps to this. The first step is to identify what type of substitution we need to do for each one of these. And there's 3 varieties. We're going to do a sine substitution, a tangent substitution, or a secant substitution. And the 3 examples we're going to do in this video, there's one of each type of example, and we'll work through those from start to finish. But the second step will be, just like with the u substitution, when we change variables, we're going to rewrite the integral entirely using the new variable, and then we will simplify. Step 3, after doing that, after rewriting the integral and simplifying it, hopefully at that stage we have an integral we now know how to do, and then we'll integrate. So step 3 in itself will be like a homework problem from Tuesday. It'll be a trig integral. And so these trig substitution problems can be lengthy because there's many steps. First we have to substitute, rewrite the integral, then we have an integral to do, and then the last step is to substitute back. Or if we have limits, we'll evaluate those if it's a definite integral. And if you remember, with u substitutions, this last step was fairly quick. Just substitute back and then you're done. It's a little more time consuming with trig substitutions. So step 4 will take a little bit more time, and so all 4 of these steps are things we need to discuss and things that will take a little bit of time when working through a problem start to finish. And again, we're going to work through 3 examples in their entirety in this video. These are the 3 examples we will be talking about, and here we have what I called a sine example, a tangent example, and a secant example. So these are the 3 varieties of trig substitutions you might see, and we'll talk about what makes one a sine example and what makes one a tangent example. But for now, let me just say, let me just tell you what substitution we're going to do, and then we can see, I'll show you why it works, and we'll see why this is a sine substitution problem. So I'm going to let x be sine theta. So my new variable is going to be theta, but I'm also going to put a 3 in there. I'm going to let x be 3 sine theta, and the 3 is because of this 9 here. And the idea that underlies this substitution is a trig identity. A trig identity you should definitely know, the main trig identity, and I'll put it in the upper right. We know that sine squared theta plus cosine squared theta equals 1. And that means cosine squared theta is the same as 1 minus sine squared theta. And if I multiply each side by 9, I'll get 9 cosine squared theta equals 9 minus 9 sine squared theta. And what this substitution then does for us is it will turn the thing under the square root into a perfect square. 9 minus x squared. With this substitution, this will become 9 minus 3. So if I replace x with what x is equal to here, I'll get the square root of 9 minus, made a mistake there, that should have been a minus back there. What we have is 9 minus 9 sine squared theta. Exactly what we have up here. This is the square root of 9 cosine squared. And so the main objective with the trig substitution is to get rid of that square root. If I make the substitution x equals 3 sine theta, it'll get rid of that square root, and that way it might simplify the integral to the point where we can evaluate it. In the second example, we will do a tangent substitution there. In the second example, I'll say x is tangent of theta, and theta is the letter we'll use for these trig substitutions. That's standard, just like we use u for u substitutions. And also, right now at this stage, we're not going to work through the integral. We're not doing the integral in their entirety. We're just looking at what substitution we'll do and why. So in the second integral, we will do a tangent substitution, but the y of that comes from another identity. We know that tangent squared plus 1 equals secant squared. So if I let x be tangent of theta here, this thing in the denominator will become secant squared. Now, it doesn't look like there's a square root here, but there is in disguise. We have that 3/2 exponent. And what's going to happen here when I substitute it in, this is going to cancel. Secant squared to the 3/2, we multiply the 3/2 times the 2, this will just become secant cubed theta. So again, what this substitution does is it gets rid of the square root. And in that way, it simplifies the integral. And for the third one, this is a secant example. And the reason it's a secant example is because secant squared theta minus 1 is tangent squared. So my substitution here is going to be a secant substitution, but there's going to be a number out front, and that number is going to be the square root of 3. And that's because of this 3 sitting here. Just like in the first example, I put a 3 there because the square root of 9 was 3. Here I'll put a square root of 3 here because the square root of 3 is the square root of 3. And so if I substitute x equals square root of 3 secant theta, that will have the effect of getting rid of that square root. What we have under the square root will be the square root. What we have under the square root would be 3 tangent squared. And we'll work through each of these examples start to finish in just a moment. But these are the substitutions we'll make, and this is the reasoning behind them. And this is all summarized in this table. And I put this table up here briefly at the end of class on Tuesday. And the way to read this table is if you see something like what's in the left column, if we see something like the square root of a squared minus x squared, and a here is a number. So if we have something like the square root of 25 minus x squared, well then we'll do a sign substitution. We'll do x equals 5 sine theta in that case. And the reason is 1 minus sine squared theta is cosine squared theta. And for the second one, if I see something of the form the square root of a squared plus x squared, that when I see the plus there, that's a tangent substitution. And the last one, where the x squared, the variable x squared, precedes the minus, x squared minus a squared, that's a secant substitution. And the reason why is given in the right column. Because of those identities, these substitutions will get rid of the square root. Now I should also mention we have the ranges of the variable, and we should. So this only comes up if we have a definite integral where we have to evaluate limits. So we'll see where this might come in, why we might need to know the ranges of the variable theta when doing a definite integral. It really doesn't come up when doing an indefinite integral without limits. I also want to point out that when we look at the ranges of theta, this is not a limitation that was not there before. For example, in the first expression, the square root of a squared minus x squared, again, let's suppose a is 5. If I have the square root of 25 minus x squared, well then x would have to be between negative 5 and 5. That's the domain of the function, because we cannot have a negative under the square root. And so the range here on theta really is not a new restriction that wasn't there before. Okay. So let's talk about step 1 of the process for doing a trig substitution. Step 1 was identify what trig substitution to do. Identify whether it's a secant or a sine or a tangent substitution. So let's just look at these integrals and see which is which. And maybe let's look at number 51 first. There I see x squared minus 9, and when you see that the x squared precedes the minus sign, this is a secant substitution. So for this one we do x equals 3 secant theta. That's the substitution we would do for that one. And 47, for example, you should look at this, and because of that plus there, the square root of x squared plus 16, that looks like, this should become fairly automatic for you between now and test 2. When you see something like this in the future, you should automatically think tangent. This looks like a tangent substitution. That might work. That might be an approach to this integral. And let's see if we could find one that involves a sine type substitution. It looks like 42 does at the very top. And so this would be a sine. So here I'd let x be sine theta. Where's another sine one? There's a few here. Number 50 would be a sine substitution. There we'd let x be the square root of 5 times sine theta because of that 5 there. And let me say, so I'm glad you're watching this video. I'm glad you've watched this far. Let's look at these 4 problems, 46, 48, 50, and 52. If you write up these 4 integrals and put them on a piece of paper and hand them in on Tuesday at the beginning of class, I will give you 5 points towards test 2. So this is like one test question on test 2. If you do all 4 of these integrals, hand them in at the beginning of class, you can get up to 5 points if they're all correct and good. Otherwise, I'll give you partial credit, of course. So write up these 5 problems, and this is in addition to the WebAssign homework you have. But it's really overlaps. These are the same type problems I put on WebAssign. But for these 4, if you write them on paper, write out all the details, hand them at the beginning of class on Tuesday, February 9th, I will give you 5 points towards test 2. And if you hand them in on Thursday at the beginning of class, I'll give you 3 points extra credit. So do these 4 problems on paper and hand those in for some points towards test 2. And what we have here are various examples of, we have a sine, a tangent, a secant. We have each example in these 4. And we also have one example in here that's none of the above. So there's 4 different types of integrals here. And again, what we're going to do next is work through some examples, and we haven't done this yet. So let's get to that. I'm going to work through 3 examples of these, and then you can try them and hand them in on Tuesday. And these are the 3 examples I said we would do. Let's do the first one. And we've already kind of started this because I said a moment ago that the substitution we're going to do for this is x equals 3. We said this was a sine substitution. So step 1 is done, and that's what we've been talking about up to now, just how to identify which type of substitution to do. But let's talk about step 2 now. Step 2, we're going to rewrite the integral using our new variable. And this is the same idea as what you did for a u substitution. A good first step after choosing the substitution is to take the derivative of each side. If x equals 3 sine theta, then dx is 3 times the derivative of sine is cosine theta, d theta. And so this tells me I'm going to replace dx with 3 cosine theta d theta. And so I will now rewrite this exact integral verbatim. It was 1 over, but now every time I see an x, I'm going to replace it with 3 sine theta. So x squared is 9 sine squared theta. Then I see the square root, and under that square root I have 9 minus 3 sine theta squared again. So I'll have 9 sine squared theta times dx, which is 3 cosine theta d theta. And right now, if you just glance at this, it looks like we've made this integral much more complicated than it was before. But it should simplify. If we made a good substitution, we know it will simplify. So let's simplify and see what we have here. This is 9 sine squared theta here. But remember, under the square root here, we had 9 times 1 minus sine squared theta, which is cosine squared theta. What we have here is the square root of 9 cosine squared theta. And maybe you can see what's going to happen there. As we said before, the square root will disappear, but also we'll get some cancellation. The square root of 9 cosine squared is 3 cosine theta times, and that 3 cosine theta d theta is still sitting there. And because I have a 3 cosine theta here and 1 in the denominator, this simplifies down to 1 over 9, and I can take that out of the integral if I like. We have 1 over 9 times 1 over sine squared theta d theta. So it simplifies quite a lot. Simplifies down to something rather simple or easy to write. 1 over sine squared theta d theta times 1 over 9. And basically what we have here now is an integral that we could have talked about on Tuesday. This is now a trig integral that you should know how to do from what we talked about previously. And think about it for a moment. I will work this one out. Pause the video if you want. But what you want to do for this integral, the best way to go about it is just to rewrite it. There's another way to write 1 over sine. 1 over sine is cosecant of x. So what we have here is cosecant squared of theta, d theta. And that's a better way to write it because I know something that has this as a derivative. Just like the derivative of tangent is secant squared, well, the derivative of cotangent is negative cosecant squared. So this equals 1/9, and then it's negative cotangent theta plus c. And I'd like to say that's the answer. We're done, but it's not. We just did the integral, but we still have step 4, which is to substitute back. The original integral was given to us in terms of x. We should write the final answer in terms of x. So we'll do that on the next slide. And I'll just write again what we had here. This came out to be negative 1/9 cotangent of theta plus c. These are equal under the substitution that we used, which was x equals 3 sine theta. That's the substitution we used. So that's what we had at the end of the previous slide. And the situation is this. I have the answer in terms of theta, but I want to write it in terms of x. So I have to replace cotangent of theta with something in terms of x. And what I know from my original substitution is I know the sine of theta. The sine of theta is x over 3. So I know what the sine of theta is in terms of x, but I want to know what the cotangent is in terms of x. And we could use identities to figure out what the cotangent would be here, but a better way, I recommend just drawing a triangle, drawing a reference triangle. I'm going to draw a right triangle. It doesn't have to be a perfect picture. Let's pretend this is a perfect right triangle, and there's the angle theta in there. And what I know right now about theta is its sine is x over 3. And I also know that sine is opposite over hypotenuse. So the opposite side from theta I could call x, in which case the hypotenuse would be 3. And if I know two sides of a right triangle, I can find the third using the Pythagorean theorem. This third side squared plus x squared equals 3 squared. So this third side squared is the square root of the hypotenuse squared minus x squared. That's the third side of the triangle. And just notice that this third side happens to be something that was in the original integral. So that's not a theorem or anything, but that always happens. And that's a way to check to see that you're doing things correctly. When you find the third side of this triangle, when you do your substitution, you should see the same expression in the integral itself. And now, with just with a little bit of work, I now would know what all three sides of this triangle are, and I can answer any questions at all. I can figure out what the cotangent is. I can find any trig function at all. All I need to do for the cotangent is remember the fact that while the tangent is opposite over adjacent, the cotangent is the adjacent over the opposite. So the cotangent of theta here is going to be the adjacent, which is the square root of 9 minus x squared, over the opposite, which is x. So our final answer for this problem, the integral came out to be negative 1/9 cotangent theta, but we can now write that in terms of x as the square root of 9 minus x squared over x plus c. So let's do another example. This is the tangent example, and we already said earlier what the substitution will be. So let's work through this one. The substitution is x equals the tangent of theta, and then the very next step, just like with the u substitution, is let's take the derivative of each side. The derivative of the tangent of theta is secant squared theta d theta, and now we rewrite the integral. 1 over, and in the denominator we have, and we've already mentioned this before, I know, we did this a moment ago, tangent squared theta plus 1, and we should know what's going to happen there. That's tangent squared plus 1 is secant squared, and that's going to cancel with that 1/2 in the exponent. But I have to finish my substitution. I don't want to forget dx. dx was secant squared theta d theta, and this gives us, I'll write it out, secant squared theta to the 3/2 power times secant squared theta d theta, which equals, we can write it as a single fraction. I'll just put the secant squared theta on top, multiplying that by 1. In the denominator, I have secant to something also, but it was raised to the second power and to the 3/2. The 2's cancel out. This is secant cubed. And so this simplifies, again, to something fairly simple to write. It's 1 over secant theta d theta. And again, this is an integral that might have been in the previous homework. This is an integral that we might find in that list on the left side of the homework from section 6.2. This is a trig integral that you should know how to do from what we talked about on Tuesday. And again, think about it. Think about how you'd go about this. But the thing to observe here is this is not the best way to write this integral. Secant is 1 over cosine. So if we have this reciprocal of the secant, what we really have is the integral of cosine theta d theta. And so the integral of cosine, that's sine. Sine theta plus c. So now we're done with step 3. We have just succeeded in evaluating the integral, which was our goal, but there's this one last step of substituting back. Let's do that the same way we did it last time. Let's do it using a reference triangle. So I'll just fit this in above here. I will sketch a triangle. I'm just drawing the angle theta, is what I'm doing, and putting a right angle here. And then what I know about theta at this stage is the tangent of theta is x, which I can write as x over 1. I also need to know that tangent is opposite over adjacent. The opposite is x, the adjacent is 1. And if I know the two legs of this triangle, I can use the Pythagorean theorem, x squared plus 1 squared equals the third side squared. So the hypotenuse is the square root of x squared plus 1. Again, we just noticed that that was in the original integral. We had x squared plus 1 to the 1/2 in there somewhere. And now that I know this triangle, I can now substitute back, because my answer that we had a moment ago, I had the sine of theta. I need to write that in terms of x, but sine of theta is opposite over hypotenuse. And so the opposite is x, the hypotenuse is x squared plus 1. So that's what the sine is, x over the square root of x plus 1. And so that's the answer to this integral. It's x over the square root of x squared plus 1 plus c. And I think I'm going, I went through that one kind of fast, and the previous one too maybe, so rewatch these videos as you need to, pause it as you need to, and with this next example, well, that's not a new one, here's the one we want. Go ahead and try this on your own if you want before I do it. Pause the video if you like. and we'll work through this one together. And so what's different about this one is, well, it's the secant. Instead of sine and tangent, we have a secant problem. But another difference is this is a definite integral, meaning we'll have to evaluate it at the end. The substitution we already said, this is a secant problem, and the reason it's a secant problem is the x squared, the variable squared under the square root precedes the negative sign. And I need a number in front of the secant. Because I have that 3 under there also, a 3 under the square root, I'm going to put a square root of 3 in my substitution. So the substitution we do here is x equals square root of 3 times secant. Dx then is the square root of 3 times the derivative of the secant, which is the secant times the tangent of theta d theta. And now, let's rewrite this integral. We have the square root of x squared. Well, x squared, the square root of 3 squared, this is going to be 3 secant squared theta minus 3. That's what's under the square root. In the denominator, I just have x, which was the square root of 3 secant theta, times dx, which is the square root of 3 secant theta tangent theta d theta. And again, this looks like a long integral, but we can see that this simplifies, and it simplifies in more ways than one. First and foremost, we should expect that square root to vanish. But before we simplify, I'm not done substituting, because as always, just like with u substitutions, we have to remember to change the variables here, the limits here. The variable x goes from square root of 3 on the bottom up to 2. We need to figure out the corresponding limits for theta. And the way we go about this is the same as what we did, same idea as what we did for u substitutions. The idea is, okay, we ask ourselves, let's do the lower limit first. When x equals square root of 3, we want to know what theta equals. Well, let's look at the definition we had for x. If x is square root of 3, that becomes square root of 3 equals square root of 3 secant theta. So we get 1 equals the secant of theta. And we want to remember that secant of theta is 1 over cosine. So if secant is 1, then the cosine is 1. And that means theta must be 0, because the cosine of 0 is 1. So when x is square root of 3, theta is 0. So that's the lower limit, 0. And this is the place where, if you remember that slide with the table of trig substitutions, and they gave us the ranges for theta. When I said if the cosine of theta is 1, then theta is 0, well, there's really more than one answer there, because I could have said theta is 2 pi or 8 pi or whatever. There's many angles with a cosine of 1. And this is what those the ranges, the range of values for theta that were given in that table, what they basically tell us here is to choose the value that's in the first quadrant or the third quadrant, whichever one applies. So here, if the cosine of theta is 1, we'll just choose theta to be 0. And let's do the other one. The upper limit, when x is 2, we get 2 equals the square root of 3 secant theta. And so here we get, the secant of theta is 2 over the square root of 3 is the secant of theta. But the secant of theta is the reciprocal of the cosine. So what we see here is the cosine of theta is square root of 3 over 2. And so theta, we think of an angle that has this cosine of square root of 3 over 2. That's pi 6. And again, I'm choosing the value that's in the first quadrant here. So now we've completed the substitution. And if you remember, I'm going to erase this to give me space to finish this integral. But if you remember, when we did a u substitution, there were two options. We could either do what we just did, find the new limits for the new variable, or the other option was, let's just ignore that for now and then substitute back later and use the original limits for x after substituting back to x. And in this case, with trig substitutions, the way we're doing it now is recommended. This is a time saver to do what we just did, to find these new limits. Because if you remember, with trig substitutions, substituting back, we have to draw the triangle. Not a big deal, but it takes a little bit of time, and we can avoid all that if we just find the new limits like we did. Okay, now let's finish this integral. What I have is the integral from 0 to pi 6. I have a fraction, I have a square root, and what I have under that square root is 3 times, I'll factor it, and when I factor I get secant squared minus 1, which is, by identity, tangent squared. In the denominator, I have square root of 3 secant theta times square root of 3 secant theta. Okay, I see something will cancel there. I also have a tangent theta d theta, and so the square root of 3 secants cancel out. And now let's take that square root. Okay, we'll still have a square root of 3, but the square root of tangent squared is tangent times, I guess I'll have a 1 in the denominator, but times tangent theta d theta. This whole thing becomes the integral of tangent squared times the square root of 3. And once again, we get an integral that, in this case, we got one that we did talk about this on Tuesday. We talked about the integral of tangent squared. That came up. So this is one that should be on our list of things we know how to do already. I'll take the square root of 3 out. But the way we're going to do this integral is to rewrite it. This is tangent squared is secant squared minus 1. And the reason that's a better way to write this is I know the antiderivative of secant squared. Okay, I'm going to go to the top here of the slide. Or maybe I'll just go to the next slide. No, I'll leave this here. Let's go to the top. We have the square root of 3 times the integral of secant squared. This won't take much space because that's the tangent. The derivative of the tangent is secant squared. So the integral of the secant squared is tangent. And then minus 1, when we integrate 1, we get a theta. And then we want to evaluate this as theta goes from 0 up to pi 6. Now let me just say a word about what we'd have to do if we substituted back. If we substituted back, I'd have to figure out what tangent of theta equals, and I would do that by drawing a reference triangle. I know, and I'd look over to my original substitution. If I know that x equals square root of 3 secant theta would then be x over the square root of 3, and I could figure out what the tangent is from that. I could look at a triangle, or I can use a trig identity, either way. But if I was substituting back, I'd also have that theta to deal with, and what theta equals in this case is, well, if secant of theta is x over the square root of 3, then theta itself is the inverse secant of x over the square root of 3. And so if this were an indefinite integral without the limits, we'd substitute these back. This is what we'd replace tangent of theta and theta with. This is how we'd go about it. But again, we can skip all of this if we have limits. We don't need to worry about that. What we're going to do is just plug in pi 6, plug in 0, evaluate, get our answer. Another comment that I want to make, when we look at what theta equals, it's the arc secant of theta. It's the arc secant of x over the square root of 3. And if you remember the domain and range of the inverse secant function, that also will explain where those range of values came from on that table we looked at earlier, and we'll look at that again in a moment. But let's finish up this problem. One more step to go. We're almost there. So I'm going to evaluate. I'll plug in pi 6, and when I evaluate, I get I'll switch colors. Oh, maybe not. I'll plug in pi 6 and I'll get tangent of pi 6 minus, I plug in pi 6, and then minus the square root of 3, and I'll plug in 0, but the tangent of 0 is 0, minus 0, that's going to be 0. Tangent of pi 6, sine over cosine. The sine of pi 6 is 1/2. The tangent is root 3 over 2. So this comes out to be 1 over square root of 3 minus pi over 6 minus 0. So this is our answer. I might as well multiply that square root of 3 through because that gives me 1 minus the square root of 3 times pi over 6. And that looks like a good way to leave the final answer for this one. So really, with a definite integral, it's a little bit less work at the end. We just evaluate like normal, provided we took the effort to find the new limits of integration, so we can avoid substituting back to x. So that's the third example. So we've worked through all three examples, start to finish, and again, each one has multiple steps. And just to briefly review. The steps are first to identify which type of substitution to do, and you can look at that table here. Let's look at that table again. This gives you the guidelines, and it also when I mentioned the range of values here, looking at the secant here, what this basically says is we should choose theta. When doing a definite integral with limits, and we have to evaluate theta, we should choose a value of theta that's either in the first quadrant or the third quadrant is what that says. And but the first step is to identify what type of substitution to do. That should become automatic with practice. And then to just like a use substitution, substitute in your new variable, simplify, and hopefully get down to an integral that you can evaluate. And then the final step, if it's a indefinite integral, is to substitute back, and we can do that using a reference triangle. And here are the three varieties of reference triangles you will see when doing these. So I'll remind you that there is a WebAssign assignment from this material posted on Thursday, and that has 6 problems in it. And in addition to that, there's also the 4 problems I said you could hand in on Tuesday, written, and if they're written up and showing all work and correct, I will give you 5 points extra credit. I don't want to say extra credit. I'll give you 5 points credit towards test 2. And if you hand it in Thursday, 3 points. So hand those in, practice these problems, and we'll talk about these next week. I'll see you next week. Thanks for watching.